Hello, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics, and today we are looking at circuit symbols, charge, and current. And the first thing I want you to do is draw and describe basic circuits, calculate current and charge, and describe how current flows in a series and a parallel circuit. So, little starter task here is I want you to copy these symbols down and name as many as you can underneath. Now, pardon me, I will make it a bit easier. So if you think you're quite confident with that in a minute, give it a go as it is. If not, in a few seconds, I will put the names on, but in the wrong order. So that will make it a little bit easier for you if you find that a bit too challenging. Okay, so there's the names. I'll give you a few seconds. You can pause it and give it a go. Okay, first one. So this here on its own is a cell. Two or more cells combined make a battery. This here is a switch, or more accurately, this is an open switch. This symbol here is a lamp, and this is a buzzer here. Next, we've got an ammeter, which is used to measure current. Then a voltmeter, used to measure voltage. This one here is a motor. This one is a resistor, and the resistor with a little arrow going through it is a variable resistor. So hope you all managed that one okay. Oops. So when you draw a circuit, use the symbol to represent a component. Pardon me. So, for example, don't draw it like this. Use the actual circuit symbols that we looked at in the previous slide. Why is it drawn straight lines? They connect at right angles, so you can see I've got like a curved corner here. Don't do that. And you should generally use a ruler and a pencil. So that circuit should look something like this. Again, here's another one which I have drawn using pictures rather than the circuit symbols. That is what it should actually look like. Okay, so quick task for you. Draw these, but using the symbols rather than the pictures like I have. A little bonus as well. One of these circuits won't work properly. See if you can work out which one it is. Okay, so that's the first circuit. If I go back to what the picture looked like now, it's a series circuit, so it doesn't matter which order you draw the bulbs and the switch. Now this here, by the way, is because earlier I showed you a open switch, sorry. This here is a closed switch. If you've drawn it as an open switch, I suppose that's fine as well, because it's just a symbol showing that it can be open or closed. Here, again, this here is what's called a parallel circuit. Next one, now this is the one that won't work because this bulb here will light up. However, this one is not a full loop, a full circuit going to the second bulb. So this bulb will not light up. So this is what it should look like if you've drawn so it works, you'll add an extra wire going from here to there. And the last one here, a little bit more complicated, should look a little something like this. Okay, so why won't some of the lights light up? Okay, so if we go through each of the circuits, now this is the one we've already looked at. So like I say, for a circuit to light up, you need a complete circuit. So when there's not a complete circuit, they will not light up. So this lamp 1 will light up, lamp 2 will not. Here the switch is open, so this circuit here, this bulb here in the circuit won't light up. Here we've got a series circuit. And so a series circuit is where you've only got one loop. This here is the parallel circuit, so a parallel circuit is where you've got two or more loops. With the series circuit, you can see that this bulb is broken, so therefore it's effectively like an open switch. So because it's broken here, no current or No current will flow anywhere in this circuit, so neither of the bulbs will light up. Whereas in this circuit here, the bulb here will not light up, but because the current can go straight from here to here to there to there, this broken bulb doesn't affect the current getting to the second lamp, so the second lamp will still light up. And conventional current is another thing to mention. So conventional current goes from positive to negative. Okay, so we say it goes from positive to negative. However, electric current is the flow of electrons in a circuit. So if you know anything about electrons, then they are negatively charged. So um, in reality, for the actual current goes from negative to positive because the negative electrons start at the negative end and they move to the positive because negative is attracted to the positive end. However, when early work on circuit was complete, scientists did not know about the negatively charged electrons flowing around the circuit. So they said it goes from positive to negative. So that's what we call conventional current. They will also not move unless there is a complete circuit, as we already mentioned. And they need a power source, such as a battery or cell, like this. So this here is a cell. Okay. Couple of questions. Now, actually, we've kind of already done this one. We've talked about which ones will not light up, but only have a go at maybe drawing these using the circuit symbols and describe why Christmas tree lights are connected in parallel rather than series. Okay, so circuit one, so I'm circling the bulbs that won't light up. Is this one and this one because they're in series. In parallel, only that one won't light up. This circuit, that won't light up. And this one here, the switch is open, so it will not light up. Draw the following circuits. A series circuit with one bulb, a cell, and one ammeter. Should look like that. Now, if you've got the bulb, say if you've got the cell at the bottom, or even if you've got it between the ammeter and the bulb, it's still fine. Doesn't matter which order you draw them in the series. A series circuit with one cell, one motor, and one buzzer. It'll look like that. Then a parallel circuit with one cell, two bulbs on the first branch, and a resistor on the second branch. So here you do, because it says you've got two bulbs on the first branch, so you have to have them here. You have to have them on the same branch, and then you have to have the resistor on a different branch. Okay. Oops. And the reason we connect Christmas tree lights in parallel is so if one light breaks, the others still work. So, for example, looking at this one here, you can see this bulb's broke, but the others still light up. Also, this is two bulbs, so it's pretty obvious it's pretty easy to find which one isn't going to work. However, if you've got a Christmas tree with 100 lights on, if one of them breaks, that's a lot of time testing all the different bulbs, and it's hard to say which one isn't working. So if you have them in parallel, you can see which one isn't working, and the rest will still work in the meantime until you change that one bulb. So electric current is the flow of electrons around a complete circuit. Electrons have a property called charge. It's why we say they are negative. So you can see that flow of electrons there is the charge. So the definition, like I say, is electric current is the rate of flow of electrical charge, and we measure it in amps, or amperes is the full term, but 99% of the time we will abbreviate it to amps. So current is because it's the rate of flow of charge, that means it's charge per unit time or charge divided by time. We use letter I for current, Q for charge, and T for time. So I is Q over T. You can rearrange that to get Q equals IT. It's how, if you're not very good at spelling, you might spell the word quit. but you shouldn't quit. So the units for current are amps, charge, it's the coulomb, and time is seconds. So here's some very quick questions for you to have a go at. Pause it, and I'll put the answer on in a few seconds. Okay, so the first two are fairly straightforward. You have to just rearrange the formula first. For the next one, you have to remember to convert a minute into seconds. So 5 minutes, it's 5 times 60, which is 300 seconds. So it's 139 divided by 5 times 60, or 139 divided by 300, gives you 0.46 amps. And here you've got it in hours. So you've got to times it by 60 to get it into minutes, and 60 again to get it into hours, or times it by 3,600. And you get 842,400 coulombs for that one. And yeah, so we've already said electric current is the flow of electrons around a circuit, and we see a current flows from positive to negative. And it's just a recap of what I already mentioned. However, in reality, electrical current is a flow of electrons. Electrons are negatively charged, so actually flow from negative to positive. Okay, so some quick questions here. At the moment, you should be able to answer question. Let's have a look. Question 1, 2, 3, and 4. You might be able to answer some of these, you might not, based on previous learning. Okay, so I'll give you a few seconds to have a go answering these ones at least. And we want to have a look now at current and resistance for a series circuit. Okay, mainly current we're looking at. So this here is a series circuit. So this little thing I've made here. So you can see I've got 120 volts and I've got 3 resistors. Each of them is 10 ohms. And you can see that the total current is 4 amps. And you can see it's the same everywhere. And you might be thinking, oh, is that because the resistances are all the same? Well, let's have a look. So I've got 10 ohms. I'll change this one to 20 and this one to 40. And you see now the current is 1.7 amps and it's the same all the way through. So this bit here in the wire, this here shows you what the current is at the wire at each stage. Okay, so that's for a series circuit only. And you can also see that the total resistance is just the 3 resistors added up, but we'll look at that in more detail in a future lesson. So the total resistance is 10 add 20 add 40, which is 70 ohms. Okay, so you can now have a go at part A. Again, pause it and I'll move on to looking at resistance, in a parallel circuit. Okay, so I'll go to 3 resistors here. And you can see here that the total resistance is 6.7 ohms. And the total current is 45 amps. So the 45 amps, you'll notice, comes here and it's split. It's 15 amps here. 15, I'll zoom in a little bit actually so you see a little bit better. 45 amps here, split into 15, 15, and 15. So you might be thinking, is it always going to be like this? Is it always the same everywhere in parallel? So what I'm going to do now is change the current to 10, 20, the resistance to 10, 20, and 40 ohms. So now the total current is 52.5 amps. So you can see that it's 30 amps here, 15 amps there, and 7.5 amps there. Most of the current is going through the smallest resistor, the 10 ohm resistor, because current takes the easiest path, or most of it will. So most of it is going through the 10 ohm resistor. Half as much is going for the 20 ohm resistor, and half as much again is going through the 40 ohm resistor. And you'll also notice that if you add these up, so I've got 30, add 15 is 45, add 7.5, 52.5. It's equal to the current in. So the current comes in here, it splits, and then it recombines here to back to 52.5 amps. One other thing to notice is the total resistance is always going to be lower than the lowest resistor here. So for example, 20, 20, and 20, which we had at the start, the total current was 6.7 ohms. If I was to increase this now to 50, so the total resistance is 6.7 ohms. The total resistance now is 8.3. It's always going to be lower than the lowest resistor in the circuit. And how we calculate that, how we calculate the resistance, is something we'll look at in a future video, which I'll be uploading soon. Okay, so you should now be able to answer the rest of these questions B and C. Okay, so pause it, finish it off, and we'll go through it. Okay, we'll go through it now. So which is the flow of, current is the flow of charge in a circuit. Which charged particle of the atom is that flows? Electrons. What are the units of currents? Amperes, usually abbreviated to amps. What's the name of the device which measures current? It's an ammeter. In circuit A on the right, name two ways to increase the current. Now, actually, if I go back to this simulation here. So to increase the current, let's take a quick look. So I've got these now all at 10 ohms. And you can see the current is 4 amps. If I reduce the resistance now, so I'm going to put this to 2, 2, 2, you can see that the current has now gone up to 20 amps throughout the circuit. So that's one way to increase it, so reducing your resistance. Alternatively, if I increase the voltage now from 120 volts to 300, it's going to 50 amps everywhere. So the two ways to do it are increase the voltage or reduce the resistance. Okay. Each of the missing currents in circuits A and B are labeled X. Work them out. So it's a series circuit here. The current is the same everywhere. So it's 4 amps. Here, I've got an unknown current going in and splits into 20 and 4. So in order to split it into 20 and 4, that means we had 24 amps going in. Diagram C shows part of the circuit. Dave thinks ammeter 1 will show the biggest current. Bob thinks it's ammeter 3. Who is correct? Obviously, it's going to be Dave. And why? Because current takes the path of least resistance, so most of the current will go through the smallest resistor. Okay, so let's have a look at some past paper questions now, multiple choice. Now this one's actually a paper one, so this is from the core paper. When the switch is open, which lamps are not lit? So it's anything on this branch. So S and T will not light, but R will. So it is D, S and T only, but that is paper one. So this is the core paper. The rest now are paper 2. Which particles move in a metal to cause an electric current? It's the electrons. Charged particles flow in the circuit below. What are the particles and which way do they flow? The particles are electrons, and they're going to flow from negative to positive. So that, in this example, will be clockwise. So the thin end, by the way, sorry, is the negative end. The bigger end is the positive end. Okay. Although if it was to ask about conventional current, it would be going the other way. The unit of electrical charge is the coulomb. A charge of 45 coulombs flows for an electrical appliance in 3 minutes. What is the average current in the appliance? So you've got 3 minutes. You need to convert that into seconds. So 3 times 60 is 180. Then you would do Q equals IT, or I is Q over T. So 45 divided by 180, which is 0.25. And that's it for today's lesson. The next one I will be uploading is conductors and insulators, and I will see you in that lesson. Thank you very much, everyone, and I will see you later. Goodbye.